past that, but our problem is only going to cover this amount right now. So we'll say somehow this cannon is buried in the ground and it's launching right at ground level. It's a new technique, the hidden cannon. So anyway, there are a couple vectors you have drawn for you. Here's what I want you to do. Here's the first vector, and I want you to call that how about that? V for vector. So you're going to have to write small. And as you can see, I wrote in some components. So here is the horizontal, and here is the vertical. I'll color code mine. You can't do that, but let's say I'll do green and blue. They'll show up. So for mine that's green, I want you to call that V sub x. Can you write small? And write that in, V sub x. Does that show up on the video, that little V sub x?
Let's see.
And the blue is the V sub y. So I want you to go across to all of the vectors that are like that and put in V sub x on the horizontal part. It's going to take me a little longer than you because yours are drawn in there. V sub x on all the horizontal parts, V sub y on all of the vertical parts. What happens at the tippy top here? What happens to the V sub y? It's gone. So on the top, it's shrunk away. So all I have is the actual vector itself is the same length as the horizontal part. And then it starts coming down. And I'm sorry, I should have had this up. Slows us down, but I'll be right with you. So that's V sub y and V sub x. And I've got one more to do. V sub y and V sub x. Alright, mine looks a little lopsided. This should be at the exact same height as this one. Alright, so what we're doing with let me see that you have them all labeled. VYs, VXs, and Vs. I'll put V on mine as well. Alright. Did you get all your VYs and VXs in? Do they fit? I know it's
I'm just copying this down.
okay. It's hard to see. I should have made that a little larger, but I can see you made a good effort here. All right, now we are going to get into the meat of the issue. Let's take a note. I'm going to write it in blue because I indicated it on blue up here. The Y components. Let's just pretend the only thing you can see is the blue. You can't see the yellow vector. You can't see the green horizontal, just the blue. So if you're just looking at these blue guys, can you tell me, it's probably even more clear on your paper, can you tell me what is happening to the blue vector on the first half of its journey? So is it growing, shrinking, growing or shrinking? What do you think, Brian, the blue vector?
Should I say shrinking?
Right, so the Y component shrinks to 0 at maximum height. So at the maximum height, it shrinks away to 0. And notice at that point, is it facing upward or downward on the first half, Emily? Number 1? Upward. Right, so it shrinks to 0, so it's a positive value on the way up. Shrinks to 0, positive direction. Hey! Welcome. Here's what we're working with today. So the Y component shrinks to 0 at the maximum height, and it's in the positive direction until it disappears. All right, what about on the second half? So what happens after this blue line, the second half? Can you describe what happens to the vertical component, Emily Davis? Oh, and Emily, number 2?
It gets bigger as
Right.
it goes down.
Right, because it shrunk away to nothing, and now it's increasing, but in the other direction, right? So it's small and then large. It's 0, small, large, just the blue, and it's going in the other direction. All right. So I'm going to say it increases in the opposite direction.
Can I interrupt to grab something?
You may certainly.
Thank you.
Increases in the opposite direction after maximum height. Alright, so that is the path of the y component in our projectile. Pretty exciting. Alright, let's switch gears and talk about the green part, the x component. And Brandon, what you have to do is, see all these ones that are in green? Under those you have to put Vx, Vx, Vx. Those are the x components all the way across. Then come back, because I didn't do that for you, then come back and grab the blue ones and put Vy, Vy, Vy across.
So the one at the top does not have Vy.
Right, it does not. It disappeared. And we made a note about that. We said the y components shrink to 0 at maximum height, and they're in the positive direction. But after that, they increase in the opposite direction after the maximum height. So that's where we were. Now we're going to look at the green guys. Now we're going to look at the x components. And this might be hard to see on my picture as well as your picture, but give it a try. Alex, what's happening to the green components? How are they changing as we go across? Are they increasing, decreasing, changing directions? What would you say about the green ones?
Well, they start increasing, decrease.
Pardon? They're starting to increase?
Yeah.
Does that look like it's getting longer? Kind of?
I don't know, depends, like.
Yeah, I know, my picture isn't exact, so what do you think,
I know, it
Zach?
just stays the same.
Ah, he hit it, never mind, Zach.
You didn't give me that as an option, so I was like, is it an option?
X
So I was like,
components
yeah,
stay the same. That's in magnitude and in direction. So they do not change, and that's pretty important to understanding projectile motion. If you break it down into its x and y components, they will always follow this pattern. The x stay the same, and the y, they decrease, and then they increase in the opposite direction. All right. Why is that? Anyone have any ideas why the x component doesn't change and the y component does change? Anybody? What's the story with that?
Well, it depends on how long you want your triangles to be on the parabola.
That's the way they fit on the parabola,
I mean,
exactly.
I mean,
So in real life,
a parabola, and you split in half, it's symmetrical,
Right.
vertically symmetrical.
right, so mathematically it
distance-
has to work this
yeah,
way to
distance-
fit on the parabola. That's good. In real life, though, what is causing it to fit on this parabola? What were you going to say?
I was gonna say that, like, if you think of x as like the distance, like it's equal distance for time, but then if you think of y as the height's gonna change because the
That's right. That's good. That's a good point. Yes.
When you say in real life, is it because of like gravity?
Yep, that was what I was really aiming for, and you hit it. Gravity does not work on anything going horizontally. It works on vertical distance. So it can pull on this vector. At first, it's shrinking it, and then it's pulling it to the earth. It's increasing it. The gravity does not affect the horizontal motion, so therefore it stays the same. So it's gravity, gravity, gravity. Another point I want to make before we leave this diagram and actually do a mathematical problem is the fact that at the end, Vy is related to Vx, so let me circle, Vy is, the beginning is related to Vy in the end. So those two, I'm going to make a note about them. These are the same in length, same value or magnitude, opposite sign. So if you were to know that this y component was 3 meters per second, you would know for sure this one was minus 3 meters per second. And that's true anywhere because it's a parabola. If this is directly across from this, you know, if you knew this was 1 meter per second, you would know that was negative 1 meters per second. So I'll just make a note of that. All right, what is before we leave and do the math, what is the acceleration of the x component as it goes across? Emily Keene, what would your thoughts be on that? Acceleration of the x component. See how I write it? A sub x. Any ideas on what the acceleration would be? Remember what happened to the velocity. So what would the, it is. So what is the velocity is the same. So if you drove here from your house and never changed your velocity, what would your acceleration have been?
Alright, so let's take a look at the board.
Yes, exactly. There's no acceleration when velocity doesn't change, when it's constant. So the acceleration in the x component is 0. So it doesn't matter what problem I give you, how much it starts at, what the initial velocity vector is, what the angle is, it doesn't matter. Acceleration in the x direction is always 0. This will simplify our work and make it possible. How about over here on the y component land? What's the acceleration into every y component? Remember what's working on the y component. So Brandon, what number? This time we're going to have a number because we're changing the velocity, so that means there is an acceleration. What would the number be? Always, when you're on planet Earth anyway.
Negative 9.8.
Very good. And that's meters per second squared, or Brandon, do you remember the feet?
32.
32, right.
Negative
So,
32.
negative 32 or not, I'm just putting up the negative 9.81. All right, 32 if you're working in feet per second squared. All right. I just also, before I keep saying one more thing before we do a problem, one more thing before we do a problem, one more thing before we do a problem. I'm going to look at not everything that you see flying outside there is going to be an example of a projectile. So if I see a fly and it's making its final journey because of the, if I see a fly going across the sky when I look out there, that does not mean that it is a projectile, because remember, the only force acting on it can be gravity. The fly is using the muscles in its wings and whatever else it has going for it to launch itself, so it has more than just gravity acting on it. If the fly stops flying, so he just stops any effort at all, and then does not use its wings or launch its body in any way, and the only thing acting on its body is gravity, it'll be going like this, then it'll start going like that. From the point where it did this, where it stopped using its own force, it is in parabolic motion. How about a jet plane? Would a jet plane be following, could we call a jet plane a projectile? Hopefully not, because once it stops, it's using its own force of its engines, it's going to fall in parabolic motion, so hopefully not. What if I throw a basketball? Is that a projectile? I throw a basketball. Zach? It is. Once it leaves my hand and the force that I exert on it has stopped, the only thing acting on it is gravity, it becomes a projectile. So anything in sports like that, football or baseball, anything like that. All right, I think I've given you the groundwork. Let's stop this session. I hope it hadn't gone too long, and we'll
Okay.
start another session once I erase the board.